Hey, you're here because you're confused as heck about related rates in your calculus class. You're going to want to stick around because I can help. So I've taught calculus for many years and I've seen firsthand the frustration on students' faces when they read these related rates problems. So I put together 3 examples that go through some of the classic type of questions you might come across. You're going to want to stick around for all the examples, especially the last one, because there's something special about the last one I definitely want you to see. All right, let's get to them. In our first example, we're going to have water leaking on the floor, and of course it forms a puddle, doesn't it? So let's read it together. A pipe is leaking water on the floor at a constant rate, and it's creating a circular puddle that is growing at 3 square feet per minute. How fast is that radius of the circle growing after 10 minutes? Now, if you think about it, the circle is going to start really small, right? And then that 3 square feet is going to be added after some dripping, and the circle's going to grow. And then it's going to grow. But every time it grows, the growth of the radius is a little bit smaller than last time because the circle is bigger. So a thin strip all the way around that circle will cause a decent increase in the area or the volume of water. Now I'm dealing exclusively with area of the puddle here. I'm not talking about volume. I could have told you that it was 1/8 of an inch deep or something, but I didn't figure that was entirely necessary with this problem. So we're going to try to figure out how fast that radius is growing at 2 different times because I want you to see how they're actually different. So let's set up the calculus here. What are we given? We are given that the area, how do I know it's area? Because it's square feet. The area is growing at 3 square feet per second. So I like to use Leibniz notation. So I'm going to use dA dt, that's the change in area as time clicks along, is +3. The area is growing, so it's positive. Now, how fast is the radius growing? So we want to know dr dt, and I'm going to put a question mark in here just to keep me focused on what I'm trying to figure out. After t equals 10 and t equals 30. So we need to get an equation on our paper that has a in it and that has r in it. Now what do we know about circles? Well, we know how the area of a circle is pi r squared. So let's write that down. The area of a circle is pi r squared. Now that we have an equation of an area, we can take the derivative and we're going to get dA dt. We're going to get dr dt because remember, they are functions, they are changing. They're not just a variable. They're a dependent variable composed of t. They're changing with respect to time. So this is the chain rule or implicit differentiation, whatever you want to think about. So the derivative of a is going to be dA dt, and now we do the power rule over here. So we throw that exponent out front, the pi is still there, the base stays the same, exponent goes down by 1, so now it's just an invisible 1 there, and we have to tack on that dr dt because the radius is changing as time clicks along too. So let's see, we were given this, the dA dt. This is what we want to solve for, dr dt, so we're good so far, but we don't know what the radius is, do we? Well, we haven't used the whole 10-minute thing yet. So let's think about this. The area at the beginning is 0, right? And then it grows by 3 square feet every minute. So we could actually create a function 3t. That makes sense? So every minute it goes up by 3. It's linear. So a of t is 3t. So the area after 10 minutes would be 3 times 10, which is 30 square feet. So guaranteed, when that picture is taken after 10 minutes, the area will be 30 square feet. All right, well, that's sort of a constraint here that will allow us to solve for the radius. So 30 equals pi r squared. Right at that moment in time, 30 equals pi r squared. So r would be 30 divided by pi all under a square root. And you could go figure out that decimal, but I'm not going to do that. I'm just going to leave it like that. So the moment in time we were talking about, 10 minutes in, the radius is going to be the square root of 30 over pi. So about the square root of 10 or so. So we put that right in here for r, and we can solve for dr dt. So let's put everything in. 3 is your dA dt. 2 pi times the square root of 30 over pi times dr dt. Remember, the dr dt is what we're solving for. So now I'm going to divide both sides by this right here. So divide by 2 pi times the square root of 30 over pi on both sides, and we get dr dt equals 3 divided by 2, and I'm just going to simplify this a little bit. If you tuck that pi under the radical, the pi's will cancel, but you'll be left with 1 on the top. So it's just a nicer way to write that. Plug that in the calculator, and you get 0.155, and the unit is a unit of distance per time, feet per minute. Feet per minute. See how easy that was? That wasn't so bad, right? We solve for dr dt by plugging and just solving. I did ask, hey, let's do it at t equals 30 and see, is indeed that radius slowing down? Let's see. So where would the 30 go? Well, it would go right in here. So instead of the area being 30, the area is going to be 3 times 30. The area would be 90 instead, right? The area would be 90. So anywhere I have a 30, I need to replace with a 90. So dr dt would be 3 over 2 radical 90 pi instead, if you work the algebra out. And that is, if you plug that in your calculator carefully, it is 0.0892. So it is slower, feet per minute. So the radius is indeed growing more slowly than earlier in the experiment. So hopefully you see how all of the different measurements in this circle are related as time clicks along, and calculus allows you to figure out how fast each component of that is growing. All right, let's look at the next example. Here we have another classic calculus problem where we have a trough, maybe for pigs or something, and it's being filled, in this case filled with water. Now let's read the problem. A farmer is filling a triangular water trough at a rate of 3 cubic feet per minute. Now the 10-foot long trough has an isosceles right triangle cross section. So after 2 minutes, how fast is the depth of the water changing? And then again, how fast is the depth changing after 5 minutes? We're going to see if those two things are different. All right, so you see my animation here, how it's filling up. And do you notice how indeed that depth is growing less and less each time because there's more surface area there for the water to get added. So that constant volume of 3 cubic feet per minute, think about it as doing like a layer on the top, and that layer is getting thinner and thinner as time goes along because of the triangular shape of the trough. So let's set this up. I'm going to draw a nice big triangle, and it needs to be a right triangle. Remember I said it was an isosceles right triangle, so that means these two sides are equal. Now we know it's 10 feet long, right? I'm not going to draw crazy 3D stuff too much here, but we know that it's 10 feet long. So that's our depth. So our height of our water is going to be this right here. So how are we going to do that, right? Well, we need to define some variables. Let's define that as h. And then in order to calculate the volume, you also have to have the base of the triangle, right? Because it's 1/2 base times height times the depth of, or the length of the whole prism. So I'm going to label this entire thing right here B, all the way across. That'll be my B. Okay, so the volume of water at any given moment is 1/2 base times height times 10. That doesn't change, does it? So the volume is V equals 5b times h. Now we've got three variables here, and if I take the derivative, I'm going to get dv dt, right? And that was one of the things that was given. I probably should have sorted all that out first, but I got so excited about the fun diagram. dv dt is our positive 3, and it says, how fast is the depth changing? So dh dt is what we're solving for at t equals 2, and then at t equals 5. So part A, part B. It feels like we need more information, right? It feels like we need some more dimensions on this triangle. But we have not used the whole right isosceles concept. Do you notice how I put these hash marks here? Because these were isosceles. So what kind of triangle do we have in here? Right in there. I'm going to draw it again for you, a little bigger. This is H, and this would be B over 2, wouldn't it? And that's a 45. We've got lots of 45-degree triangles in here. So what is true about the two legs in a 45, 45, 90 triangle? They're equal. This is one of the cool things in this problem that you need to realize, is that B over 2 has to equal H. Now in that equation, V equals 5BH, I would really love to get rid of B, right? Because I just want dH dt. That's what I'm solving for. I'm going to get rid of B. So I have to multiply by 2 on both sides. So B is the same thing, is equal to 2H. So now I do a substitution, and I can come over here and write V equals 5 times 2h times h, or V equals 10h squared. At all times on this trough, the volume is always 10 times the height squared. We haven't done any calculus yet, by the way. This is where we're going to do the calculus. This is where the dv dt is going to come out. 10 times 2 is 20. Base stays the same, exponent goes down to a 1, so that's nice. What do we need to do? Put that dh dt there at the end, and that's what we're solving for. dh dt is going to always be the rate of volume divided by 20 times the height. So let's come back up here. At t equals 2, what is the height? Because we need it. You see how the height is in this formula. Well, once again, kind of like the last problem, we're going to have to figure out the height by figuring out the volume. Because remember, it started empty, and then after 2 minutes, how much water has been added? Well, the volume is 3t once again. So the volume would be 6 cubic feet at that moment, after two minutes. So 6 equals 10h squared. That came from over here. So h is the square root of 3/5, or 0.6, the square root of 0.6. dv dt divided by 20 times h. So dv dt, remember that was 3, divided by 20 times the square root of 3/5 is our dH dt. So if you go to your calculator and put that mess in, you're going to get dH dt equals 0.194 feet per minute. Feet per minute. Remember, because it's a measure of distance, kind of like that radius was. So it's feet per minute. All right, so what about at t equals 5? Now, just like we did previously, we're going to have to use the volume of 15, because 5 times 3 is 15 cubic feet have entered that trough. So we use our equation, 15 equals 10h squared. So h is going to be the square root of 15 over 10, right? And we put that in the equation just like we did previously, and we will get dH dt, I know I'm running out of room here, dH dt equals, and it is 0.122 feet per minute. All right, that's slower. That's slower, and that makes sense. Again, you saw it in my animation, but when it's filling up, yes, it's filling up, but the fill rate almost feels like it's slowing down, even though it's a constant volume going in. And that's because there's more surface for those water molecules to spread out on. So the change in the height slows down. Here we have one last problem. This is my third example today and final one. And this one has that little trick I mentioned in it that you do not want to miss. So let's read it. An 18-foot tall streetlight casts a shadow on a 6-foot person. And that person is walking away from the light at 3 feet per second. So how fast is the tip of the shadow moving? So you can see from my little animation here that the tip of the shadow is moving faster than the person. So we expect to get an answer higher than 3 feet per second. Let's draw a triangle set up here nice and big so you can see what's going on. This is 18. Here's the person, and they are 6. All right, we want to know how fast this dot is moving. So let's call this entire distance right here, let's call this x. And then this distance over here, I usually call d, the distance that the person is away from the street light. That means this distance in between right here, what would that be? It would be the whole minus the part, so x minus d. Now, where do we go from here? That's all the information we have. We have that d dt is 3 because the person's distance away, that red part there, that is changing with a positive 3. We're trying to figure out dx dt, but we don't have anything else other than the 18 and 6. So what's the trick? What is the trick? Similar triangles. Look for similar triangles. Sometimes you look for Pythagoreans in these kinds of problems. Similar triangles. Now, what do we do with that? Well, we write a true statement. That's called an equation, right? 18 is to 6. So the big is to the small triangle. You see the small triangle here? This one right here. This is the small triangle. 18 is to 6, big is to small, as x is to x minus d. Look at that. So we have an equation on a paper, which we can always take the derivative of equations. I think I want to cross multiply first and maybe simplify before I do that. So I get 18x minus 18d equals 6x. I'm going to move all the x's to one side, 12x, and I'm going to move the d's to the other, equal 18d. Divide by 12. X is, and this would be 3d over 2, right? 3 halves. 18 over 12 is 3 halves, 1.5. Now what do we do? Boy, we are so close to the answer. Do you realize how close we are to the answer? Take the derivative. dx dt, because x is changing according to time, is 3 halves. The d goes away, but you put your dt over here. Now, what were we given? dt, it's kind of fun to say, is 3. So dx dt is 3 halves times 3, which is 4.5 feet per second. Do you notice that there's no variables in that expression at all? It's not growing. The tip of the shadow is traveling at a constant rate, just like the person was walking at a constant 3. The tip of the shadow, the very top of it, is traveling faster, but at a constant rate of 4.5 feet per second. I find that really interesting because I would have thought that tip would be accelerating. It just seems like it would, you know, but it's running at a constant rate, 4.5 feet per second. So there's the 3 classic related rate problems that I could come up with to kind of show you how, the different types work. Hopefully you found this video helpful. If you did, hit that little bell icon, like and subscribe this video, and leave your comments down below. I always love reading them. All right, until next time.